Okay, here we are looking at the answers to the practice test. All right, let's take a look at some of these questions here. All right, when the energy of a system is higher after a reaction than before the reaction took place, the reaction would be called endothermic. So, endothermic means heat goes in and the system is higher in energy. Now, whether that's a dissolving process, a melting process, chemical reaction, endothermic means the products have higher energy. Number two, in any chemical or physical process, either energy is neither created nor destroyed. That's the law of conservation of energy. Number three, study of energy changes in chemical reactions is called thermal chemistry. That's what this whole unit is about. The study of energy in chemical reactions. Number four, for an exothermic reaction, energy exits the system and flows into the surrounding. Exothermic heat goes out. Number five, the Greek letter triangle, that's called delta. It's a capital Greek D, corresponding to D, stands for change in. So delta T in this unit, and there's lots of things that are delta in chemistry and physics. In what units is temperature measured? Well, of course, degrees Celsius. Could be degrees Fahrenheit, but we really didn't talk about that. All right, number seven. Energy is measured in units of joules. Could also be measured in units of calories and food calories as well. Number eight. A piece of paper burns and gives off energy. This is an example of an exothermic. All right, anytime something burns is exothermic. We call that combustion. All right, delta H for that process. Delta H for that process would be a negative number. A negative number meaning exothermic. Number nine. A chemical reaction is taking place directly below a beaker of water. If the temperature of the water increases by 15 degrees, what's happening? The reaction system gave off energy and put it into the water. All right, that's just like the Cheeto lab we did. We took a pop can and we burned a chunk of Cheeto underneath it, and the heat energy went into the water that was inside of the container. Ice cream's dropped on the floor. As it melts, it's undergoing. So the ice cream must absorb energy, must take in energy. That would be called endothermic. Number 11, endothermic reactions have a plus or a minus value, Q value. All right, now endothermic. All right, now we could talk about Q is in terms of MC delta T. So if it's endothermic, then Q is a positive number and the heat goes in. Now, as far as the delta H for that type of reaction, all right, that's going to be a positive number for endothermic. All right, so the heat that goes in is positive and the delta H is positive. For exothermic, the heat will come out and that'll give you a negative amount of energy, and then delta H will be a negative number, exothermic. Negative delta H, or a loss of heat, decrease in heat. All right, those are the first few questions. All right, question 13. A student does an experiment and determines that the metal easily changes temperature. Which metal did this student most likely study? Well, these numbers tell you, basically how easily something can absorb heat. So whatever one's the smallest number, which is lead. A student does an experiment, determines the metal is high resistance to change, so it takes a lot of heat to make its temperature change. So that would be the one with the biggest number, beryllium. Number 15, write the word heat in the correct location for the reaction below, which has a delta H that is a negative number. That means it's exothermic. It means that it produces heat. So if we put that inside of a chemical equation, we're going to put it on the right side of the arrow. Heat is produced. All right, now if delta H happened to be positive, then we would put heat on the left side of the arrow. And then you'd have all the other stuff in there too as well. All right, so your reactants plus heat when it's endothermic, and for that kind of reaction, delta H is positive. All right, we have some calculations, and we've got two equations. We've got Q equals MC delta T. Now, on the test, I think we're going to give it a little differently. I'm going to write it as Q equals MC delta T. They're just in a different order here on this test. I think the practice test you guys had it in the right order. And then we also have Q equals N, which is the number of moles, times a value called delta H. All right, so N is moles, and delta H is a energy in, say, kilojoules per mole. Kilojoules per mole. All right, number one, calculate the specific heat capacity. That's C. We're looking for C in the equation. The temperature of a piece of glass goes from 12 to 26, so we've got a delta T. We have a mass, M, and we have a Q, energy. All right, so those are the things that are given. We're trying to find C, so we got to take our equation and solve it for C, do a little algebra, and then we put in our numbers. Our data has 3 digits, 4 digits, 3 digits. Let's round it to 3 digits. All right, question 2. How much heat energy in kilojoules is required to raise the temperature of 142.5 grams of acetic acid from 41.5 degrees to 62.7 degrees? The specific heat is 2.50. Now, specific heat is C in the equation. All right, so we have specific heat. We have the specific heat C. We have delta T, subtracting the two temperatures. We have M, the mass, and we are trying to find Q. Q equals MC delta T. And everything is in the right units, so we can calculate. Now, how many digits do we have? Our temperature technically has 3. This should be rounded to 16.19 kilojoules. Now, it's said to put it in kilojoules. So when we do this equation, we end up in joules. So asking for kilojoules, just move the decimal. Number 3, how much heat in joules will be released? 6.4 grams of carbon is used according to the reaction below. All right, now looking at the delta H. Delta H, it gives off kilojoules per mole. All right, so the amount of heat then is Q equals the number of moles times the delta H. N times delta H. Now, N stands for moles, but we are given grams. So we got to do a little bit of conversion. This goes back a couple of units. The molar mass for carbon from the periodic table, 12.01. So instead of 6.4 grams, we'll use 0.534 moles. Now we can put it into the Q equals N times delta H. Moles times kilojoules per mole gives us kilojoules. 3 digits, 4 digits. Let's round our answer to 3 digits in kilojoules. All right, question number 4. It's a little tricky because it has multiple questions built into one. Now, we have these delta H values that are given in kilojoules per mole, and they're telling us that the mass of gold gives off 24 calories. Since the delta H is given in kilojoules, we're going to want to convert our calories into joules. So first we'll do that, taking 24 calories and multiply it times 4.184 joules per calorie, and we'll get this converted into joules. Now that's the heat given off. That's going to be Q. And then we're going to use the delta H that is given. Now I see there's an error in this calculation here because the 45.92 is in kilojoules and the top here is in joules, so we would have to move the decimal over here and make that 0.100416 kilojoules, and then that's going to make the answer be 0.002187. Alright, so that'll change this, 0.002187, and that's going to make that as 0.4307 grams. Alright, so we did this calculation and solved for N, but they ask what is the mass, not the number of moles. So we'll have to do a convert from moles to grams using the molar mass from the periodic table. Okay, this problem is a lab-based question, and we have some data here collected in the lab. And this is like the Candle lab or the Cheeto lab, whereas we have a container, call it a calorimeter, which contains some water, and then we burn something underneath it. Does it say what we're doing? The following experiment? A taco. We are burning a taco. So we're putting a taco underneath there and burning it. They tell us the mass of the taco. They tell us the mass of the water that's inside the container. They tell us the two temperatures so we can tell what delta T is. And then they give us the specific heat of water, which is usually always known. So the questions. Number 1, calculate the change in temperature. That is our delta T. Take the final temperature minus the initial temperature, the change in temperature. Number 2, calculate the change in energy in the water. So the burning of the taco will heat up the water, and the water will gain heat according to Q equals mc delta T. M being the mass of the water, C being the specific heat, also given right in the data table, and then the change in the temperature will answer from number 1. That'll tell us how much heat the water gained. How much heat the water gained. Now, question 3, kind of a trick question. How much energy did the taco produce as it burned? Well, if the water gained that, we're going to assume that all that energy came from the taco. All right, so the taco gave off. Now, that's our assumption. It might be a little bit of a stretch, but our percent will probably not be 100%. All right, number 4, calculate the energy in joules per gram for the taco. Well, the number of joules the taco gave off divided by the mass of the taco will give us the joules per gram for the taco. That would be like what's on the label if you looked at the label of some kind of food. All right, now, in the United States, we measure food in calories per gram instead of joules per gram. You go to any other country, you'd probably see it listed as joules per gram or joules per serving, and then they'll tell you how many grams are in a serving. So question 5 says, calculate the energy in calories per gram. So we got to know how many calories are in a joule. All right. Maybe we remember that 1 calorie is 4.184 joules. Or we could say that 1,000 calories is equal to 4,184 joules. Or we could call it 4.184 kilojoules. All of those things are true. Now, so we just convert from joules into calories. All right, now there's actually a typo here in question 6. That's why it says there that it should say 2.18 capital C calorie per gram. All right, because they're talking about a food calorie. All right, so that's like a kilocalorie. So to convert that into a small c calorie, we'll just move the decimal 3 to the right. And then we use the percent error calculation, whereas the theoretical value is that, and the experimental value is what we got right there. Times 100 makes it a percent. All right, there we are.